amount of content about this topic. Here we go. Vector databases. I was actually surprised about the content in this topic. I didn't really know that vector databases existed prior to RAG. I hadn't really heard about them or why they might be used. So it's pretty eye-opening for me. Let's see if we can change slides here. So personal motivations, I see a lot of commercial applications. Currently, I also have been toying around with some personal projects, and that opened doors for me. And thirdly, like I see all these mentions on AI Twitter, and I'm like, what are these people going off on? So hopefully some of these things like clarify main ideas and terminology for anyone else that is curious. So in terms of commercial applications that I've been seeing, there's a lot of RAG. So I'll go more into that, but you essentially supply relevant documents to the query you're asking an LLM like ChatGPT, and that's going to improve the performance and reduce the hallucination. I've also seen recommender systems. So because vector databases help you find similar documents to what you currently have, you can give a user, hey, like here's an image that's like the one you just liked. Here's a movie. There's also applications for search bars. So if you can find documents that are similar to a query, that's just like kind of like a Google-like interface, or inside of a company's web page, how do you find the relevant results to the query? So distinguishing vector databases from traditional databases. In a traditional database, you could have SQL and you could look for exact matches to what you were searching for. It's more along those lines. In a vector database, you're more explicitly storing like a vector of ones and zeros, and you're more explicitly looking for similar matches to what you searched for. It's not about this like exact match. I'm looking up user Steve and all of the transactions associated with Steve. To me, that's like a traditional database. Steve shopped at Amazon 18 times. Here's all of the records that occurred. This is more like Steve looked up a cat image, and what are other images that we can give Steve? What are like cat products we could give Steve? So in a vector database, you want to be doing approximate nearest neighbor search, and it's optimized towards doing that because you have like, let's say, billions of vectors. And some of the techniques that it's achieving that are hashing, quantization, and graph-based search. So it helped me to finally like see a flow diagram of what is happening with RAG, for example. And in the orange left of the center, you'll see the vector DB. And so in a flow, let's say if you're talking to ChatGPT, a new plant, if you want to supply ChatGPT with a relevant document when you're chatting with it, the way that that could occur is that you have a vector DB and you have a query from the user. The query from the user is going to be transformed into an embedding, which is then going to be, it's going to ask the vector database with that embedding, what are the most similar documents to the query? And then you end up with, like, let's say this is a prompt. You're talking to ChatGPT, and at the start, in order to improve the results, you could say you're an assistant trained to answer questions using the given document. The relevant document that the vector database helped supply could be put into that context, and then answer the following question. And there's the query that originally came from the user. So this presentation is not primarily really focused on RAG, but I want to supply like a basic example of RAG and how vector databases flow into that pipeline. I've been curious about like the context window size that's supplying documents to an LLM, about how it's been growing and like how much, like they mentioned the token max window sizes. And I was like, okay, what is that in practical terms? Apparently now for GPT-4, you could put like a book or two into the chat, like worth of content. I'm seeing nods from my noobs. That's good. And previously GPT 3.5, it was like, let's call it a 10x improvement. Let's be a little optimistic. But yeah, the prompt context window size and the amount of tokens you can stuff in seems to be growing more and more. I suspect that this benefits RAG. I haven't seen like whether you're able to get good answers if you supply RAG with an entire book of information. Like, is it better if you just give it like a paragraph that's relevant? I would guess. But I do think it's interesting that you're able to supply more and more information in the context window. An area I want to focus on in this presentation in that flow diagram for RAG is the embeddings. So the magic of the vector database is in finding similar documents or images to your query, because you're storing a bunch of vector embeddings, and in embedding space, things that are nearby are semantically similar. So probably a lot of people, or most people in this group, are familiar with this. If not, that's fine. Like if you know NLP and you know like word2vec and how embeddings are able to have similar semantic information nearby points, that is like the magic that helps vector databases retrieve you semantically similar information. So to give an example, in my master's degree, I did a project trying to re-rank YouTube API recommendations for videos. And I was actually using it to filter them down based on a user's preferences. So I used SentenceBERT as my embedding model. And I also used OpenAI Ada. And this example taught me that your choice of embedding model actually means a lot for your use case. So in my case, SentenceBERT is optimized to have really high cosine similarity when two video titles or sentences are semantically similar, and very low cosine similarity if they are not. It's like operating on that extreme scale. And when I was querying OpenAI Ada, if I put together two random things, it still had 0.7 cosine similarity. So I was not seeing that it was working for my particular use case. Very recently, I saw OpenAI release text embedding 3 small and large. So we have new embeddings that have higher benchmark scores. In particular, there's a miracle benchmark, and they improved from 31% to 54%, which is a pretty big jump. Also, I saw it was interesting that you can reduce the sizes of the embeddings that OpenAI provides with a technique called MRL. And I think that's important because if you have a vector database and you are used to using a certain embedding size in your pipeline, like you can trim down the OpenAI embedding to be of a certain size and still retain most of the utility. So that was cool. I don't know if Anoop knows this guy, but I follow this guy on Twitter, and I thought it was cool that he pointed out, I think he works at OpenAI, that you can embed an entire book for less than a penny. So I think it's a good portrayal of the efficiency of the marketplace right now for embedding things. Other aspects that are interesting to me when thinking about embeddings are knowledge cutoffs and the dimensionality. So we can see that text embedding large is, let's say, twice the size of embedding small. So it would seem to me that the more dimensions you have with the embedding, the more semantic information you can capture. But also look at how embedding small and Ada are the same size. It would seem that embedding small was used a different technique, and so that's why it's doing better on the benchmarks. Also, the knowledge cutoff seemed to be September of 2021. I wonder why. Like, maybe, like, is it hard to get information post September 2021 because of some regulations? I don't really know. But that does affect your use cases if it's more current, like culturally relevant information or whatever else. Yeah, Yonatan.
I just had a question. So,
Yeah.
question for everyone. So, when you say embedding, that's the last hidden state from the last transformer block, of some language model. Is that what embedding means?
Good question.
Before
So
like the input?
I don't know how OpenAI supplies it. I just know I make an API call. In my case, when I use sentence BERT, um, I the output of the sentence BERT was an embedding of fixed size. So that's what's going on when I used it. I would pass in a sentence, and the output of the function call um, would be a vector of a fixed size. Yeah, maybe
Does
someone else has like a better explanation.
yeah. Yeah, no, that's it's interesting. I don't actually know. I was curious if someone knew how the embeddings are
Yeah,
derived.
I don't think they reveal like exactly, but it does end up being just like activations from some layer trained on some similarity loss, right? Um, but yeah, I think the exact way it's trained or like the architecture, which exact layer they're actually dumping is not exposed.
So when you say similarity loss, so I mean I know models like CLIP are trained to the contrastive loss, but um, when you so would you need like would you need to fine tune the language model or use some other pre-training objective? Like what do you guys know about this? Or could you just use a language model and like it would be fine? You would get reasonable embeddings.
I So we actually did something similar at Neuro where we're trying to find, let's say, similar like object behaviors. Like, so for instance, if there's a bicyclist who's cutting off the car, can we take an embedding from our prediction model or a planning model and then try to find similar such cases? And I think it actually works reasonably well without you even fine tuning on the similarity
Mm,
loss function, like contrastive loss or triplet loss or whatever. Um, I think in this case with like the OpenAI models, they definitely do train with the similarity objective function. I don't know the exact details, but I would guess like you're saying something like clip probably.
got it. So it sounds like I know there's probably a lot you can't say, but it sounds like maybe you start with a base model and then fine tune it with a contrastive loss or something. That sounds reasonable.
Yeah, I think something like that.
Thank you.
There are certain papers I've found that take general decoder models and extract embeddings from the last hidden state. And that is it's an open area of research.
Okay, interesting. Yeah, I think in the case of sentence BERT, it's an encoder. But yeah, interesting to see like the possibilities with the decoder as well. Um, Another interesting Twitter commotion I've seen recently is there's an approach to embeddings now called Colbert, and I don't know who runs the Stanford NLP group Twitter, if that's like if I'm following like a real account, but their stuff's cool, and yeah, the Colbert goes in a different direction where you have instead of having a single embedding for what you're trying to pass in, you get multiple embeddings, and it helps you like I didn't have a chance to fully understand Colbert in the slightest, but yeah, it helps you to get better results and also optimize for speed. So something to pay attention to in the near future if this continues to be a useful approach.
Do people know how many embeddings it returns, and like is that tunable? Like is K, I don't know, K in my opinion, or my, I don't know, my literal intuition would be like, 3 to 10. Does anyone have more of an understanding on what multi-vector embeddings mean?
It seemed to me that each token has its own embedding, and then it has a function that's able to compute what the overall meaning of the sentence should be. So it's somehow aggregating a lot of different embeddings to still get like one representation for, let's say, a sentence that you packed in. I would be really excited to dig deeper into this, but I just wanted to briefly mention it as like a new direction that people are researching.
Yeah, I would be
Yeah.
super curious, like what the impact really is of like having embedding per token versus just making your embedding larger, maybe capturing more salient information. Because the OpenAI embeddings are already pretty large. I think it's like 3072 dimension.
Yeah.
So yeah, I don't know. Also, it makes it difficult to like dump all the embeddings in a vector DB if it's per token, right? So there's probably some scale considerations there, but yeah, super
Yeah.
curious trying it out.
I don't know who Mark Tenenholtz is, but he has good posts from time to time. He seems to have strong feelings. Yeah, sorry, I don't want to trigger. I know he says don't use OpenAI as the baseline. I don't feel any sort of way about it. Just thought it was interesting.
I
Okay.
have a little bit of background about like the Colbert like paper.
Oh, okay. Yeah.
And if I remember correctly, it's basically they like instead of summarizing the entire document into a single embedding, they keep all of like the tokens and their own embeddings. Because if you look at like a transformer, basically it just like it for every token, it just keeps updating the embeddings for every token, basically. And so they just keep the last layer embeddings for every token in a document. And then when you have a query, they basically compare like every token in the query with every token in the document. But then I think someone raised like a concern about the scalability of such a thing. And like in the paper, they sort of discuss that by saying they have like a new like pruning technique that doesn't require them to check all of the tokens from all of the documents, but just a little bit of them, like something like 0.3% of all the tokens to get some really good like retrieval. So I think like this is how they do it. And it's actually an old paper, by the way. Like Colbert is like it's built on like the BERT paper. It's like a 2020 paper. But I think that like the mechanism is like pretty, I guess, like robust and good, to be honest.
Okay, awesome. All right, thank you.
I can send you the like the link to the paper in the chat if anyone's interested.
Sure. Yeah. So I also, I was poking a lot around like documentation. Pinecone is a vector database company. I was interested in how they recommend matching like the embedding similarity metric that you use to the one you use to train the embedding. So for example, I use the first one there. That's a sentence BERT. You're supposed to use cosine similarity, and they recommend that in their docs as well. There's some BERT-based .v5 that apparently you're only supposed to use dot products for. Versus on the OpenAI, I know that their recommendations pertain to their own systems and API calls, but they say cosine similarity, I guess, for speed, but that you can find a way to use multiple different options here. So I have a personal example. I was traveling and I wanted to work on a project for English to Spanish translation. And I had experienced that some Google Translates I was getting were getting like funky like output predictions that didn't seem like real Spanish. So as a project, I thought, okay, if I have like an English phrase that I'm trying to query Google Translate, what if instead I could find like the most semantic, like nearest neighbor in English to what I'm looking up that has a ground truth translation to Spanish. So I don't have to trust an AI black box prediction. I can know, okay, I want to say this in English. If I say this equivalent thing in English, here's the Spanish translation. So so Sam and I were working on this, and effectively we used SBERT, and we created embeddings for the English, and then we were doing a brute force cosine similarity search to find the highest cosine similarity English phrases to other ones in the data set. And as we were like testing out if this was scalable, it started becoming very, very slow. And this posed an interesting question: what efficient vector similarity search algorithms are there? So by digging into Pinecone DB's documents, I learned some techniques that are used in vector databases to make this efficient, to do approximate nearest neighbors. So they use product quantization, PQ, local sensitive hashing, LSH, hierarchical, navigable, small world, HSNW. I had never heard of any of these before. It's possible that if you come from like a different hardware, CS or something background, these are all obvious. Yeah, coming from data science, didn't know about these things. So product quantization was pretty interesting to me. It's pretty fascinating. So apparently you can split your embeddings into partitions of a fixed size, and then you can run k-means on those, and then index only the cluster centroids. So you're keeping a fraction of the original data point information, but you're keeping a highly useful fraction, which is like the k-means clusters themselves. And then once you have a new query vector, you can find the distance of it to the centroids, and then you can decide from which centroid you want to retrieve nearby vectors from by looking for the lowest sum of squared Euclidean distance. So yeah, this kind of opened my eyes. I didn't know that this like partitioning of embeddings thing was possible. And yeah, storing the cluster centroids is a cool trick.
Well, one question about this. So
Yeah,
is the point of doing k-means just to reduce the number of like candidate nearest neighbors? So you only have to like search for search over k vectors, or
let's say you wanted to like find a real cool city to visit. You want to find something really exciting to do. Like instead of searching over all restaurants in all cities for tomorrow night, then you could just store like the cities, like some aggregate point of information. That's the centroid is like when you store a centroid, I think you should also store somewhere else the reference to the points nearby the centroid. So you're searching like a higher level of information, and that once you have channeled yourself into, okay, I'm next to these centroids, then you can see, oh, there's these restaurants are in this city, and like search further within the centroid.
right? Yeah, makes sense.
Do people
But
know?
yeah,
Sorry.
go ahead.
Do people know how they choose K?
I didn't see that in the docs. And it seemed to me, so from a big picture, this is managed by the Vector DB, and the Vector DB will also optimize the hyperparameters for multiple algorithms, PQ and other ones, based on the scale of your data and other information about your data. So yeah, it didn't provide like, okay, like if this is true about your data, use this K. It seems that the Vector DB, yeah, will do that like hyperparameter search for you at this stage of the technology.
Thanks. They probably don't publicize their secret sauce.
Yeah. One thing I thought about is like vectors, like you could have one user who has a completely different use case from another, but the fact that it's just like a calculator, like some vector computations to me seem like they'll reoccur across different use cases, different customers, but you should already start learning about how vector space is like split up naturally. And so I think like some of these, if you have hyperparameter tuning for one customer, it may be useful for the next customer. I'm speculating about math that I'm not an expert in, but that's why I think like if you're hyperparameter tuning, if that's in their secret sauce, like why it should transfer from one situation to the next. Okay, so there's also LSH hashing, and I thought this was interesting. Like in a general like dictionary hash function type situation, you want to like avoid collisions. Here they flip that scenario. You actually want to maximize collisions. To me, it seems like you want to maximize collisions because you want things that are highly similar to be grouped together. And this approach is actually combined traditionally, they say, with shingling, min hashing, and banded LSH. Pinecone did not elaborate on what those were, but good to know. Secondly, there's an approach with random hyperplanes, and I'll get into that in a second. So, yeah, so Yonatan could probably explain this better than me. But in the random hyperplanes situation, there's a property of mathematics that was shown that if you take a dot product between your vectors and a random matrix of a lower target dimension, that the similarity between your points, if you do this for your whole like vector space of a bunch of embeddings, like the similarity, the distance between the different embeddings will still be preserved, which is cool. So this is like a compression technique that preserves most of the information. And Pinecone mentions that doing this, like truly doing this with a random matrix, can be computationally expensive for large data sets. So I think it might have been an indication that, and also because they say that this is not the traditional approach, that this is not necessarily what they're doing themselves. The founder of Pinecone is Ido Liberty, and he's known for JL transform research, which to my understanding is this property that like using a random matrix to compress your vector space is like a safe thing and a smart thing to do. So yeah, so to me, it seems like they took the company in a different direction than the research originally led them to.
So do they use the JL transform in practice, do you think?
I didn't see any mentions of JL transform. I think, yeah, I think you and I, like, when you shared that paper with me, that was like more math than I can understand. I think that's how we were talking about like using the random matrix, right? And then you were like, oh, JL transform. So yeah, I didn't see any mention of JL transform in their docs. Yeah. I think maybe it explains like the founding vision for the company. So that's probably why they give a lot of space to this in the website. Yet, like, to me, saying it's not the traditional approach and having your own research as a second bullet point could be either way. So I also discovered apparently there's a difference between a vector database and a vector index. So Pinecone explicitly compares themselves to Meta's FAISS, as Adi pronounced it to me, FAISS vector index, the Facebook AI similarity search. Yeah, vector index. So that is a benchmark to them, and they want to emphasize that they, above the FAISS vector index, they can provide to you, the data storage, metadata filtering. They're going to manage your services versus the FAISS is like an open source library. So this, yeah, I think you would partner with Pinecone and they would deal with most of the scaling and security and data backup issues for you. And all of the techniques that we just described, so these are from Pinecone's website. And I was also seeing these in FAISS. So I think they may use many of similar techniques to FAISS, but they want to like sell additional services from managing your data. So FAISS. So FAISS, there's a blog post from 2017 that I posted in the WhatsApp group. And basically they made a huge leap where they built a k-nearest neighbor graph on 1 billion high dimensional vectors. So this was an impressive like production system approach that stood out from the crowd. Like there were a lot of research based approaches for searching vector space, but they were for way smaller scale versus this open source library has been like, there's even a paper from 2024 about FAISS. So the library's been going strong, and they evaluated over a deep 1B billion image data set with Euclidean distance. They use k-means, PCA, PQ, which we discussed, and LSH and HNSW as well. So the things that I saw on Pinecone's website are also associated with Fife for a while now. So I toyed around with this. My friend and I tried to do some RAG in Jupyter Notebook. And yeah, you can create your own FICE index in Jupyter Notebook, which was cool. The default is Euclidean distance. So what I was saying earlier is you got to be careful like what kind of embeddings you're using. And I think for what I was using, you're actually supposed to use cosine similarity, but with LangChain, the default was Euclidean, and I didn't see in the docs a way to change that. So yeah, something to be careful for like in practice and production is like what default similarity metric these things are using. So FICE, the considerations in that blog post about why their system was highly successful. They tried to optimize for speed, memory usage, and accuracy. And they want to compare it to the brute force approach, which is like where you, kind of like I was doing with Sam, where you slowly compare one example at a time. You want to avoid that. You want to use the compression techniques to do approximate nearest neighbor search and still retain most of the accuracy that you would otherwise get. So 2 metrics I learned about from this, then in that blog post, they use one recall at 1, which is the number of queries for which the true nearest neighbor is returned first. So in a brute force approach, you end up eventually after 1 billion years discovering, oh, this sentence is the most similar of all sentences to what I queried for. But you don't have 1 billion years. So one recall at 1, when you do have some brute force baseline information, helps you understand, like, do I still get the best possible answer? And what % of the time does that occur? There's another metric called 10 intersection measure, which is the average fraction of 10 nearest neighbors in the first 10 results. So in some use cases, you care about having more than like the single best nearest neighbor returned. To me, it comes to mind like Google search. You have like a page of like results. The user like scans through them and decides, oh, number 7 is actually the one I want. Okay. And then the system rewards itself because it was still in the top 10. Because the user is not going to go to page 5 of Google search. They're going to like stay within the first 10 results, let's say. They provide this graph in the blog post for FICE on the benchmark data set of Deep1B. And they explain that the prior approach for that benchmark had a 1 recall of 1 of 20 milliseconds per vector. And for 45%, 1 recall at 1. So that means that like 45% of the time, the true nearest neighbor is returned first, which is really cool. So previously that would occur at 20 milliseconds per vector, and then they actually lowered it. This is like a log scale or something. I think they lowered it to 2 milliseconds per vector. So that is a huge improvement. Another thing to note that their vector index is able to do is that you can set a target accuracy. The accuracy is on the x-axis here, and FICE will optimize the system search time towards your target accuracy. So it would seem that in the open source code, you could tell it, okay, I'm comfortable with an accuracy of 25%. Give me the best possible inference speed for that. Yeah, okay. That's the end of the presentation. So yeah, happy to address any thoughts, questions, corrections. Yeah.
Yeah, very nice, man. Would you be able to go back to the previous slide where you talked about the metrics?
Yeah.
So one recall at 1. So brute force is like the ground truth, right? That gives
Yeah.
us the true nearest neighbor. And
Yeah.
then you're measuring how often is it, what is the proportion of queries for which I'm actually finding the true nearest neighbor. And when you say return first, so I guess you're returning multiple candidates.
Great question. So yeah, so that makes me wonder whether it gives you like, here's the top 10, or I think it gives you the actual Euclidean distance. And the library said a few things. It supports giving you, okay, here's what we think is the top one. So it's approximate nearest neighbors, right? So I think the distance it gives you is correct, but it won't even calculate the distance for all vectors. Approximate nearest neighbor seems to be that you're only going to only evaluate a fraction of the possible vectors in the data set. I think you're still able to calculate the correct Euclidean distance or cosine similarity between 2 points. That was a long-winded answer, but I hope I was helping answer the question.
Okay. So
Yeah.
one recall at K or something would be the number of queries for which the true nearest neighbor is among the top K or something.
Yeah. Okay. So it will evaluate over way more than one, because that's how it gives you the best candidate it does. So yeah. So I think you can modify the K and okay. Actually, let me look that up later. Because it's one recall at one. So one of those represents queries and one of them represents the fact that it's returned first. So I wonder what 3 recall at 1 is, and what is 1 recall at 3. So let me look that up later to make sure.
I'm assuming that like you have some input vector, you want to find the K vectors nearest to it in the database. Phi
Yeah.
gives you an approximation to that list of K vectors. And they're sorted by distance, right?
Yeah.
So phi tells you, here's what I think the K closest vectors to you are, and then brute force is the actual closest.
That's my understanding. Yeah.
Cool. Very nice.
Yeah, I had a quick question actually. I know you mentioned you created a RAG style application before. I'm curious,
Yeah.
like just plugging in a vector DB worked, or if there are like optimizations beyond that, like having some sort of hybrid search instead, or adding a re-ranker on top, or like what did you kind of need to do to actually get it to work?
Oh, this was like a small toy project, just toying with like LangChain, like in like a small Jupyter notebook, Anoop. So yeah, if my friend and I end up like building it further out to improve the results, I'll let you know.
Yeah.
But yeah, I just wanted to get my hands wet with like, toying with these libraries, because I can read about them, a lot, but I wanted to actually like see, okay, can I actually use FICE, or do I need like a billion vectors and like a bunch of hardware to do it? Apparently you can just do it in Jupyter Notebook in your MacBook. So that was cool.
Gotcha. No, makes sense. I think
Yeah.
one of the things I've noticed is like we built something like I was mentioning at Neuro, doing this sort of similarity search, and a lot of times it just doesn't work out of the box. Like you need to add some sort of filters on top. Like, so you need offerings of a traditional DB where you want to have some metadata filtering. Maybe you want to kind of combine both types of search and then do some ranking on top. So yeah, I'm honestly a little bit suspicious of the whole embedding search hype train over the last 2 years, because I feel like just traditional search does get you pretty far, but yeah, the semantic understanding portion is definitely helpful for higher recall in some of these cases.
Okay. Yeah, that makes a lot of sense. Like, I can't speak for Meta, maybe a D can, but like if you want to find similar images, you're not gonna like compare it to all images Meta has ever had. You're gonna like maybe pass it through a classifier and then like reduce the search space a bit based on some like actual like labels that might be in a database. Here's a cat, here's a human, and then after that you have a subset that's like relevant to actually compare in a vector DB. Maybe from there. Okay, makes a lot of sense. So yeah, Pinecone DB has metadata filtering. So they say that that's something they do that the Vice vector index doesn't. So
Yeah, makes
did
sense.
you guys use Pinecone? Like, I don't know when you were doing a new did you use like a different system?
Yeah, we use Pinecone at Neuro.
Oh,
yeah. I think the other cool thing about Pinecone actually is they have two different types of indexes. So one is more storage optimized. So I think the algorithm that they use is actually like a disk-based ANN algorithm. But the query times are like maybe 3x longer. And then the other one is like performance optimized. So it'll be like an in-memory vector search algorithm, maybe probably like HNSW or something like that. So it seems like they've like really specialized their offering for different use cases.
Okay. That's awesome. Yeah. You only learn so much from reading like the docs in like the emphasized docs. And then when you actually implement systems, you see like what they're truly doing versus like some of this might be like, the marketing version. Yeah.
Yeah, thanks for the presentation, Gabriel. I had a question, yeah, for you and maybe anyone else who might know. I guess like you presented basically like three different methods, right? So remember correctly, there's like locality sensitive hashing, product quantization, yeah, right, and HSNW. So how are these like combined? Is the idea that you pick one depending on the use case, or like you end up doing all of them? Like I believe like FICE supports all of them, but yeah, just curious, like yeah, do you end up picking one or like somehow
Yeah.
combine the benefits of all?
Okay.
Yeah.
Okay. So with what I did in Jupyter Notebook, you literally like in one line created FICE. So I didn't have to specify any algorithms. And also Pinecone says, hey, we use these, but behind the scenes, we combine them and we optimize towards your particular data, and we hyperparameter tune and the such. And in FICE, in their docs, they say that as well. Like based on the particular data, the code will like decide like how to optimize between these. And great question. Like mathematically, like these seem like fairly different things. Like what is the connection between all of these? I do wonder that.
I think you can combine them. Like for instance,
Yeah.
I know Weaviate is another vector DB where their default search algorithm is HNSW, and then you can optionally elect to choose product quantization to reduce reduce memory usage of your actual vector index, and also to just like reduce number dimensions so it runs much faster.
Okay.
Got it. Cool. Yeah. And then like maybe a follow-up is like roughly as a rule of thumb, if you're using one of these approximate nearest neighbor algorithms, what's the complexity of like building the index and then querying it? Is it like presumably it's like log the number of entries like multiplied by the dimension size or something like that?
I am not sure. I did not see that in the docs. But that is a great question.
Yeah, I think the FICE paper, which I can quickly link, has some derivations on this, but yeah, I didn't like really read it in close detail.
Yeah, so there's a FICE 2024 paper. And I think there's also like a 2017 paper.
Right.
Personally, I wonder like Yeah, it'd be cool if that was known, like a known fact, like what is the complexity? Or is this all like empirically shown to work? Like, okay, you've massively reduced the search space by like doing clustering, and like here's the number of milliseconds you end up with. Like, okay.
Yeah, I do think the real-time aspect of this is pretty interesting. It's like, do you need to recluster as you get more and more data? And like, what is the cost there, right? Like, how long do people have to wait for that data to be ingested in your DB? I think for Pinecone, at least for the storage optimized one, they do actually recluster everything. So there's like a few minutes to a few hours delay, which they've actually mentioned to us before onboarding us to that index. But for more like HNSW type applications, you can, I don't know exactly what the time complexity is for indexing, but yeah, roughly scales with number of dimensions, and your vector is like immediately available for search with like right after it's ingested within a few milliseconds.
That's pretty interesting.
Nice.
Yeah, the FICE, so that last slide I had, yeah, the FICE says that you can tell it what accuracy you want, and then it will optimize for the speed, and not the other way around, where like I want this speed, and then you end up with some accuracy. So not sure. Maybe you need to experiment. Wait, so when they warned you, like it will take a couple hours, like how often would that like occur? And like, was that when you added more data? Like why was that happening?
Yeah, basically our use case was like extremely write heavy, but very low queries. So we'd have billions of embeddings that are being dumped. And we don't need them to be in memory, and it's fine if queries take like 500 milliseconds or whatever. So they came out with a new version of their storage optimized architecture where reclustering would happen every hour, let's say.
Yeah.
So the data just wouldn't be available. I don't think it's like, I don't know if there's a lot of variance. Like, it's not like sometimes it would take a few minutes, sometimes it would take a few hours. It's just like we tell them the requirement that we're okay with it taking 3 hours, and they kind of kick off clustering along those time periods, I think.
Oh, okay, interesting. I wonder if like one k-means run like helps like to speed up the next k-means run, or if it needs to like go from scratch. I'll have to read about it. Okay.
Yeah. One question I had is, I think so. Yeah, my understanding or my intuition is that like there are some specialized applications where you would want to use a vector database, like if you're building some kind of search, whether that's embedding search or some kind of application that leverages search. But if you're just trying to do RAG, like it seems now that OpenAI has like implemented RAG that you probably don't need a vector database. Is that currently correct? Like, does that agree with what you guys have seen?
Maybe a noob knows. I mean, I've only used like the API call to get the embedding from Ada, so I didn't know that OpenAI handles like RAG. So
Yeah, I guess my question is basically just like, in what situations would you want to use a vector database and like roll your own from scratch versus like just use OpenAI's RAG?
what's OpenAI's RAG? Yeah,
I think the RAG offering is still kind of limited though. It's like, so there's an assistance API that we offer where you can upload files and your queries will be kind of, your context for the queries will be stuff with relevant snippets from those files. But then the number of files you can upload are limited. And also, I guess people want to like own their own, if you want to use an open source model or something, you kind of want your own vector DB, things like that.
Right, I see. Makes sense.
Yeah, open source can save a lot of money. I was at a conference and one speaker said like if you use Llama instead of OpenAI's, it's like a 30x
Wow.
cost savings. So if you have the data science expertise and that fits your use case, that's definitely a very reasonable thing to do. But those are data science expertise is hard to come by.
Yeah, I've actually heard though that it's actually hard to beat the price of like GPT 3.5. Like unless you like have a very large amount of like utilization of your of your GPU that's running Llama, that it's like actually quite hard to beat 3.5. I think if you're comparing to GPT-4, for example, then like maybe you can more easily save money. Yeah, I guess I've heard different things, but good to know.
Yeah, fair enough. That's all I know. So thanks.
Yeah.
Yeah, I think it is, I guess, back to Ali's question of like what happens to vector databases. I think it is an interesting question because like you see players offering more managed RAG solutions, right? Like maybe eventually, like, I don't know, LangChain offers like a managed solution and they build a vector database as a component in that, or OpenAI is doing that right now. And also B, you see kind of traditional databases starting to offer support for nearest neighbor search directly. So there's like PG vector extension that you can plug into Postgres and like that will do the search for you. So yeah, I'm curious what kind of happens to all these things. Like, did all these just become commoditized and like, or do they just get eaten up by like, some other DB like Mongo or something, and like they just offer it as an extension? Or yeah, I'm curious how things play out here.
Hopefully we'll get cheaper and cheaper and faster. Okay. We're at the hour. Any other anything else come to mind? Okay. Yeah, you want to tell anything else to talk about with like future meetings or how that LLM WhatsApp bot went?
Oh, yeah, maybe Adi or Anup can comment on that, but they ran some experiments with the WhatsApp transcript. But yeah, so next week we're gonna meet as usual. Mazen is gonna be presenting on a topic. Maybe you can give us a teaser on that now. And yeah, other than that, I think that's it. Thank you very much, Gabriel.
Dude, thank you for everyone for participating and bringing in like extra like industry knowledge. That's pretty impressive.
Cool.
I guess
Thanks,
like
Gabriel.
the teaser for next week would probably be yeah, we decided to venture a little bit into vision, but still LLMs. So next week it will be on a recent Google paper on called like spatial LLMs. I guess a major critique of language models now is that they have no like understanding of like physics or geometry or any like other like spatial like characteristics because they're trained on like text from the internet. So yeah, it might be interesting to see how Google like try to solve that problem, I guess.
Awesome.
Thank you.
All right, guys, I guess we'll end here and we'll see you all next week.
Well, thank you guys. Hey, Adi, can I talk to you after for a minute?
Yeah, for sure.
Okay.
Cool.
Thank you,
Maybe
Gabriel.
just thank you guys. Yeah, maybe just end recording.